Thank you, thank you. I appreciate y'all having me. So one thing that I forgot to put on there that I'll talk more about at the end is I interned at TVA for 2 years while I was going to school at Tennessee Tech. So I'll talk more about that at the end. James is in our group now, so hopefully he's saying good things about TVA and the internship program. But I would highly encourage you all to consider, even if it's not interning with TVA, but interning with a company before you go into the real world, is what everybody would tell me. But until you go into a full-time position. So again, I want to make sure and have some time at the end. So if somebody can just let me know when we have like 15 minutes left. And then I can, because I've got a lot of slides, but I want to make sure and cover that at the end and make sure that there's time for questions too, if y'all have questions. So again, thanks for having me. I've been at TVA for almost 20 years now, including my internship. It's been a great career. I've enjoyed it. Of course, I'm very biased for TVA. It's a big company. It's not perfect. No company is, but it's made a lot of progress in the past few years in technology and innovation. When I first started at TVA as an intern, we were kind of a leader, I feel like, and I think a lot of would agree in the industry. We were a leader in innovation technology, implementing new technology in the field, and then things kind of died off. Probably around 2005 to 2010. Of course, we kind of hit a recession then, and funding was harder to come by. But we kind of lost our position in the industry for innovation. The past 5 years, we've really become more active in the industry. You've probably heard, or you may have not heard, we used to call it Grid 2023. And then we decided, you know what, we want to go beyond Grid 2023, so we call it Grid of Tomorrow or Grid of the Future. But the focus of it is to really promote innovation, and not just for TVA, but also for the industry. TVA is one of the largest public power utilities that are out there, and because of how we're structured, where we own generation, we own transmission, we can do a lot that maybe some of the market companies can't do, or some of the smaller utilities can't do. So we're trying to leverage that for the industry and for sure for the Valley. So, all right. There's a lot of slides behind this. This is what I want to try to cover today. Probably won't get through all of it, but I'm hoping I can get through most of it. And again, I want to get to the intern program and tell you a little bit about that. So, this is an overview of TVA. How many have heard of TVA in here? Hopefully. And it's okay if you haven't, because I'm also on the intern and university advisory board at TVA, and of course we've been having a lot of WebEx fairs and interviews, and we find folks a lot of times that haven't heard of TVA, even living in Chattanooga, and that's okay. That's okay. We're trying to get better about promoting that, but I always ask that question. So you probably know a little bit, sounds like a lot of us in here know a little bit about TVA, maybe a lot, but this is our service territory that's shown on the map here. We serve 7 states. Some of them are just small pieces, like North Carolina, Virginia, very small pieces. Most of Tennessee we serve, except for just a small piece up here in the top corner. I can't see that, that's okay. 80,000 square miles, 10 million residents. So again, this is kind of a high-level overview of TVA. For our mission, it's really generation and power delivery, environmental stewardship, and economic development. Again, we're a little different than a lot of other utilities. We're a public power utility, so we're not here for profit. We're the largest public power utility. So we don't have investors. We also do a lot in the environment, which not all utilities do that. And then economic development, of course a lot of utilities do economic development. You bring in new industries, you bring in new loads, That's revenue. It helps the economy in the area for jobs. So TVA has been a strong leader in the industry with bringing in different types of industries and jobs. So, whether it's polysilicon plants, automotive plants, we try to work with them on providing low wholesale rates so that, that helps their profit margin. All right, so transmission. I guess, is it kind of a mix in here with engineering, double E's? How, I didn't know if this was all double E's or just engineers.
I have some computer engineers, but
Okay.
close.
Okay, and it's okay even if there's, we like civil engineers too. I'm just kidding. But if civil, mechanical, TVA has a big pool of engineers and computer science majors. But I guess this is, in my mind, is a little more focused on double E's and I guess even civil. But we have over 16,000 miles of transmission line, and a lot of them are 161,000 volts. So you've probably seen some of these structures here with the steel lace towers. We call those steel lace tower structures. We've got pole structures, we've got concrete structures. But you've probably seen those riding down the road. They're usually huge right-of-ways, 200-foot, 250-foot right-of-ways. And so you'll see some of those that are 500,000 volts, but a majority of our 16,000 miles are 161,000 volts. Of course, what normally serves your house is much lower than that, even before it drops it down to 220. It's 7,000 or 13,000. And so that's one thing that also is different about TVA, if you're not familiar with. You guys don't write a bill, pay a bill to TVA for your power consumption. You usually pay it to the local power company, EPB. There's several, Volunteer Electric, Sequatchie Valley Electric. So TVA serves down to 153 local power companies, and then they serve down to your house, to the residential meters. So, all right, I won't go through a lot of this. All right, so I've done this presentation a lot in the industry and at a couple of universities. Who has heard of PMUs? Has anybody heard of PMUs? And it's okay if you haven't. It's relatively new. What, Synchro Phasers, PMUs, has anybody heard of that technology before? Okay, it's okay. Well, this may be tough on some of the pop quiz questions, but it's all right. You don't get graded on this. So does anybody have a clue what it stands for? What the acronym PMU stands for?
Power Management Unit.
That is a great guess. That's
Phase manipulation?
Boy, you guys are good. They're wrong, but they're good. Those are good. I wouldn't even have come up with that. You're close. Both of you are close. All right. Phaser measurement unit. Again, this technology was first developed by, I don't want to give that away. That's one of my pop quiz questions. We'll get to that in a minute. It's only been around for probably 30 years, 20 years where it's really been utilized, and it's still relatively new. One thing that I have learned in the power industry, it's kind of slow to evolve. You have the medical industry, automotive, a lot of that seems to do pretty well with technology catching up. The power industry, in my mind, and I think a lot of folks will agree, is always behind. And this is no different. This is something you would think, what? We're just now doing this in the industry, but it's advancing. It's just slow. It's slow. Okay, what does a PMU generate? Again, another pop quiz question. These may not apply as well since a few of you have been exposed to this. Synchro Phasers. So that's what I want to talk about today. So this is a PMU box shown here, Phaser Measurement Unit box. It looks, what it is, it's essentially just a laptop in a box. That's all it is. But it's getting values from out in our substation. So what is a synchro phaser? That's the value it's getting. What, does anybody have a guess what is a synchro phaser? So it is a voltage and current phaser. If you all haven't learned, especially double E's, about current and voltage phasers, you will. But in this case, it's measuring the voltage and current phaser out at a substation, and it has a timestamp with it. So it's not just that it's measuring it, it's putting a timestamp with it and sending it somewhere. It's sharing that. And that's key, and you're going to see that later, why it's so key to timestamp these measurements instead of just, you know, measuring it and sending it somewhere. You have to have the timestamp with it. Okay, so I kind of touched on this earlier. Who invented it? It was Virginia Tech. 1988 was the first PMU, or synchro phaser device, that was developed. There's even some arguments over this, but this is the most consistency I've seen is Virginia Tech. So see, in 1988, and we're still, I mean, it's still kind of evolving out into the industry. Again, I feel like the power utility industry is a little slower to adapt. So, but once we get there, we're good. So this is the way analogy I use. We have Scada. You'll hear folks talk about Scada, which is data that our operators use. I work in transmission operations at TVA. We work with our operators. They're down at workstations in a bunker or underground. They're the ones that are opening and closing lines, bringing on generators, you know, out in Memphis, North Tennessee. So they're all working from workstations using Scada data. So it's telling them this switch is closed, this breaker's closed, this generator's putting out this much, you know, in megawatts. And so they're using all of this Scada data to make decisions. It's great. It measures voltage and current as well, but it's really slow. It's about a sample every 2 to 5 seconds. And it's not time stamped. So you may be getting something that is, I don't know, 30 seconds late from Memphis telling you this breaker just opened or this breaker just closed or this unit just come on. It's what has been utilized in the industry for years. And so it works, it's just, it's really slow, and again, it's not time stamped. So what the analogy here is everybody kind of says, well, it's kind of like an x-ray. You know, it gives you some visibility, but not a ton. PMU data, synchro phasers, again, it's a sample it's 30 samples every second. Some places we have it's 120 samples every second. So it's much higher resolution and it has the timestamp. So again, the analogy here being that's more like an MRI. You get a lot more detail from what the grid is doing compared to Scada data. This is a video. This is the top video here, or the top screen chart is synchro phaser data from a PMU. The bottom is Scada data. I think this is voltage values. Yeah, it's voltage values measured at the same location, okay? So it kind of gives you, let's hope I can get this to work, kind of gives you an idea of how they differ. Remember, sample rate here is 30 samples a second. This is one sample every 2 to 5 seconds. So you can see what's going on here. Oh, I'm sorry. This is a touch screen. Sorry. I'll keep my hands off of it. You can see what's going on here with the voltage. Something's going on at the substation, and it's seeing this like oscillation in the voltage signature. Scada, nothing's changed. So if you're an operator, this may work in some cases, but wouldn't you rather see this to know? I mean, the average here is you know, what your mean is here, and it's not changing. Now it jumps up almost like a step function, and you see it, but you're missing a lot of the story here, and that's the beauty of synchro phasers from PMU devices. Okay, this is a very high-level diagram of how it works. You've got a box. Remember I told you it was the laptop in a box. That's the device, the PMU device. It has current and voltages from a substation feeding in this box from a potential transformer and a current transformer. They go into this, they go into this device, but remember how important I said it was for a timestamp. So we have a GPS clock at each substation that provides a high resolution timestamp, and it feeds into that device as well, the PMU. So you've got three things essentially that are feeding into that PMU device: a current phaser, voltage phaser, and a time clock signal from your GPS clock. And that all goes across a network. These are our control centers at TVA, and then they go into our end users here, which we'll see later. RTDMS is our real-time dynamic monitoring system. So some of the applications that we have started using at TVA and in the industry for Synchro Phaser technology is oscillation detection and alarming. We'll talk more about that later, where we've seen units that started swinging their output almost uncontrollably, to where we were worried there was going to be damage to these units, especially to the rotor shafts, where you put a lot of stress, torsional stress on the rotor shafts. Using them for NERC validation or NERC standards, how to meet some of the NERC standards to show that you're compliant. Post-event analysis, we have big events, storms. We've had several storms in the past couple of months, and we've used PMU data to go through and be like, okay, this breaker opened, this substation went in the dark, and so it gives you that type of detail. You can determine sequence of events. Equipment failure detection. Man, wouldn't it be great to know when we're getting ready to have a transformer or something blow up? And I mean, that happens, I won't say quite a bit, but it happens, where you have something that's 50, 60 years old, some of them may be 10 years old, and they have a short and they end up exploding or failing. And so that's where the industry's headed. We've all seen it. Our roads are getting old, our bridges, our transmission system's the same. It's old, some of it's 67 years old infrastructure. So we have things that fail a lot. All of us do, not just TVA, but the industry. And we can't replace it all. But when it fails, it usually puts you in the dark, or it puts me in the dark, or all of us in the dark. And if we could use this technology to say, this transformer's acting up, you might want to go check on it before it fails, before it puts people in the dark. So that's where a lot of this type of data is headed, is trying to predict equipment failure. Phase angle monitoring, alarming, we'll talk more about that, and linear state estimation. That's, again, kind of like replacing Scada. It's using PMU data to replace Scada to give you high resolution data, high visibility. This is our map. So I showed you those little boxes. Everywhere there's a dot, that's where we have a device. And right now, this is old. It says, I think last fall we had 165 devices. We probably got over 200 now that are online and streaming. So we have them at our substations, and if you've ever seen a relay panel, I may have a picture in here. They just slide in a relay panel, the PMU device, and then you hook up the connections to the PT, CT, and the GPS clock. And then they'll start streaming. You have to have a big server somewhere. We have several big servers downtown, and that's what they do. Remember I showed you that we had the PDC phaser data concentrator. All it is a big server, and it takes all the PMU data from Johnson City over to Memphis to Starkville to Bowling Green, and it time aligns everything because it's got a timestamp for every value that comes into TVA. So the beauty of it, and you'll see it in a minute, is if you have a big tree fall in a 500 kV line in Johnson City, that ripple effect, that voltage ripple effect or whatever it may be, can be seen through the valley with the PMU data. You may see where your voltage phaser dips a little in Starkville, Mississippi for something that happened in Johnson City, Tennessee, because all of it is time aligned. And you'll see that on some of the videos. All right, this is, again, we've got a couple devices. This is a standalone PMU. This is a PMU, I call it a laptop in a box. both that do the same function. This is an old PMU, that ABB, that we no longer use. And everything is kind of, you know, what's interesting, again, the industry's lagging a little bit. Your phone, you use it as a cell phone, a camera, a computer, you know, there's so many, it's a lot of functions in one box. That's where the industry's headed, to where you used to have a relay box, a meter box, a digital fault recorder box. It's almost getting to where in the power industry, you're trying to fit as many functions in one box, because that saves space on relay panels. That's less money you got to spend. And it can do all these different functions. Now the bad thing is, if it goes kaput, you just lost everything, you know. But that's where it's headed, is where we're having PMU devices that are also digital fault recorders, where of course those are triggered when you have a fault on your system, and they give you high resolution data too. A PMU is always streaming. Digital fault recorder, it has to have some kind of trigger event. PMU streams all the time. They are data hogs. So you gotta have big servers to pull in all this data and store it. So the more devices we add, the more server space we gotta have. We try to keep about a year's worth of Synchro Phaser data. This is a PMU Dashboard. We worked with a local company here in Chattanooga that helped develop it. It essentially tells you, each one of these is one of those boxes. It's telling you, is it working correctly? Are you getting data? The purple one shows, you know, hey, there's a clock issue. The clock keeps coming in and out, the clock signal. Remember, you got to have a clock signal for it to be Synchro Phaser data. So this thing's old here too. I mean, remember I said we've got over 165. So this is one of the first prototypes of it. But it looks the same now. It's just a lot more boxes. But we have network operators that monitor this. They monitor Scada, they monitor network communication, and they're on shift just with our transmission operators as well. They do shift schedule, and they have a lot of servers, a lot of networks that they're monitoring. And if you ever get the chance to go into the control room at TVA, the one at the dam, you walk into a room like this, and it's just wall-to-wall video boards. And they have tons of diagrams and dashboards like this that they're monitoring. It's a little overwhelming, but that's what they're doing. They're looking to see when these change state, call the field engineer, hey, this one looks like it's failed, or the clock's going out, I need you to go look at it, and they assign a ticket. So there's a lot of O&M to keep this going. This is pretty popular now. I should have brought one, but I didn't think I had time. This is called a micro PMU. It's a little box. I mean, I guess you can kind of tell the size. It's probably 6 inches by 8 inches, and they're mobile. So they're different than the boxes I showed where you put in a relay panel. The difference is, I don't know if you can tell here, this little black box, that is a cell phone antenna. This right here is a GPS antenna. So that's, you know, you've got your cell phone antenna to transmit the data back to our servers. And you think, well, why don't y'all just use these everywhere instead of using that box that I mentioned you slide into a relay panel? Well, the problem is with cell phone, you've got delay with your data transmittal, right? You've got some lag. So you could use it for post-event analysis. You can use it for going back and look at historical events. The problem is you can't operate to it from a real-time perspective. So our operators can't operate off of this type of data because it has such a high lag. But it's okay. If you want to use it to record, like this was being installed at our Sequoia nuclear plant because they were having problems with their exciter on one of their units. And they kept saying, this is transmission. You're doing something on the grid. It's causing my unit to misbehave. And we said, no, there's nothing we're doing. We're not switching lines in and out. We're not, you know, doing anything in the area for maintenance. You know, you're pulling our voltage down. But we didn't have the high resolution data from Scada to show who was flinching first. And once we got this PMU in, this micro PMU, we could actually see that their exciter was moving first, their megavars were moving out of the unit first, and then our voltage was following whatever the exciter was doing. So we could show they were moving first, and then our system grid voltage was following. So it was that there was the proof there was something going on with their exciter. And we did this about 3 or 4 years ago, and then we ended up buying several of these because now we can move them across the valley when we're trying to troubleshoot and install it, and then move it somewhere else if we need to. So this is the data that comes out of it. One thing we've seen is models. Y'all probably, if you haven't dealt with models, you will, or you'll hear about models. How do you model a transmission system with impedance values? You know, we have to build these big models. There's models of the whole Eastern Interconnect. The problem is a model is only as good as the data that goes in it, and our models aren't perfect, and they don't always align with how the grid responds. So there's a NERC standard that always is challenging, requiring utilities to verify your model of how you model your transmission system, TVA, it matches up with how the actual impedance of the grid for your system. So if you have devices like a PMU, you can record it. You can record how your megawatts from your output of your unit respond, and then how your units actually respond in your model. Is your model accurate? Is your model responding how it is in reality when you have a fault on the system or when something changes and you open or close a line? Okay. Combined cycle plants. TVA, if you've seen it in the news, we've been retiring a lot of fossil plants and installing a lot of gas plants. And a lot of them are combined cycle plants, which is a gas turbine coupled with a steam unit. So the gas turbine, of course, will burn natural gas, and then it will be used to heat up a boiler for a steam unit and turn a steam unit. So Paradise up in Kentucky is a 3-on-1 combined cycle plant. 3 gas turbines that just, again, burn natural gas, and then they heat up steam to be used on the 4th unit to get megawatts. So we got 4 units that are outputting. It's about 1,000 megawatts or so. And so this is relatively new. We installed this combined cycle plant. We put a PMU device there, and this is our software, RTDMS, Real-Time Dynamic Monitoring System. It takes those PMU values and it looks for something erratic, you know, like what we call an oscillation. So you don't want your units to be going up and down a lot. You want them to be stable. And that's what this software is looking for. It's looking for something that's abnormal with the unit because, well, one thing, it could move the voltage around a lot to where our customers can use it. 2, it can cause damage to the actual generator. I mean, if you think about rotating the shaft one way and then slowing it down, speeding it up, there can be a lot of fatigue and stress on the rotor shaft, and it can end up causing damage or loss of life for the unit. So we turn these units up. They're brand new, 3-on-1. That's what the 4 boxes are shown here. And not long after turning it up, commissioning the plant, we got PMU data in. We started getting an alarm in this software, and this is seen by our operators. This is what our transmission operators use to monitor the grid. Okay, one of the pieces of software. Remember Scada, there's all kinds. But this is what they're looking for. They're looking for these oscillations that could impact reliability or damage equipment. So they got this alarm, Paradise CT3. You can see it was in 2018. I think this plant was commissioned in the spring. This is the actual detailed PMU data, Synchro Phaser data. And it's the voltage values for all 4 units. So this is the steam unit that I mentioned. These are the 3 CTs. Does one look a little different than the others? It's not drastic, but you can tell it's noisier. So that's what this software was alarming off of. The PMU data is coming in and it's saying, there's something going on here. You need to look at it. And that's why it went into alarm. That's why this turned red. That's what there's several annunciation and alarms that go off to the operators, but they have this in front of them. So my group went in, looked at it, and that was the phase voltages. Then we looked at just CT3, which is the one that went into alarm, and these are the line-to-line voltages or phase-to-phase voltages. And in a balanced system, if you haven't learned this in your EE classes, you will. These should be on top of each other. There shouldn't be a difference here. Well, they are. There's a difference. You see the B2C, the gold, is shifted down, and so is the green. They're not. They should be on top of each other, and they're not. So that was telling us something was off. So we called the plant and said, you need to look at this. We're getting an alarm. I don't know what's going on. And they said, perfect. We're getting ready to take a plant outage. They do outages quite a bit to do maintenance work during the spring and fall when people aren't running their air conditioners and heaters as much. And so they said, we'll look at it this fall. And they did, and this is what they come back with. This is a fuse. I don't remember what voltage it is, but it's a fuse. It's probably about that big. I don't know. I think it's like maybe a 2,000 or 3,000 amp fuse. And this is the fuse holder here. And you can see it's missing part of the holder. The connection is gone, has arced away. And you can see on the end of the fuse here, this is the fuse cap. I think this picture shows it. There's been some damage to the fuse cap. And what had happened was this was not seated properly and it was arcing. And that's why we were getting this very noisy voltage signal here. So the unit wasn't oscillating like we thought it could be, but there was something wrong there. And this was a great catch because had this failed where this fuse would have fallen out and it would have tripped the unit, it would have cost TVA quite a bit of money, potentially damaged some equipment. So we got lucky. We thought it was a unit oscillation, which we'll see in a minute. That's not what happened here, but the Synchro Phaser data and the tool caught this, which was good. And now we know how to look for it. Remember I talked about equipment failure detection? This is a perfect example. We weren't really focused on equipment failure detection here, but that's what we ended up finding. Browns Ferry Unit 3. Browns Ferry is a nuclear plant that we have in Alabama. So there's 3 units. Now they're about 1,300 megawatts apiece. We went and did an EPU, extended power uprate, and I'm not a nuclear expert, but the way I understand it is they redo the steam piping and valving. So you've got a unit and you're trying to make it more efficient on how it utilizes steam, and you can get more output, megawatts. Everybody wants more megawatts. That's more power to sell and generate for our homes. So each unit was uprated 150 megawatts. So they went from like 1,200 to 1,350 or so a piece, which is a big bump. So that's 450 megawatts extra TVA got by doing these steam revalves. So the first one was Unit 3. They went through an outage, did all their work to make it more efficient, get a higher output. They brought it back. We had a PMU there streaming Synchro Phaser data. Within, I don't know, a couple weeks after them bringing it up, they brought it up real slow. It's not like they just turned the switch on. It starts out at 0 megawatts and they would go up to 500 megawatts, let it sit for a week. Then they'd go up to 1,000 megawatts and let it sit for a week. And somewhere around 1,000, 1,100, we got an alarm for Unit 3. And, again, what's going on here? So this is a video of the output. This is the megawatts that the Synchro Phaser data is provided coming from the PMU for Unit 3. And the teal is Unit 3 output. The gold is Unit 2. So Unit 2 never came down. Its outage was later. Remember, this unit was done first for getting the higher output, but I wanted to show both Unit 3, which is coming out of this outage to get more megawatts, should look like Unit 2, okay? So you're going to see what happens here as they're bringing the unit up to its full output power, which is around 1,300 megawatts. I sped this way up. So you can see they're bringing the unit up, right? Its output levels is gaining. This is noise. This is kind of normal. But look, something's happening here. You can see the peak-to-peak value is growing. So this is what RTDMS, the software we just saw on the previous slide, is alarming to. It's saying there's an oscillation here. You know, what's going on? So we started getting the alarms, and as they're bringing the unit up. So we're at about 1150, well, no, 11. A little over 1,100 megawatt output. So they're still bringing the unit up. Remember, its new values closer to 1,300 now. So it's going to be higher than Unit 2. Now the oscillation is growing even more peak to peak. And again, this is not good because what it relates to is that torsional stress on the rotor shaft. So this is 30 megawatts peak to peak. That's not good. Especially for long durations of time. But as they raise it up, can you tell if you look at kind of the boundary, the envelope of the signature, it's going down, and then it stopped. So we knew something was going on. We reached out to the plant, and it's fun working with a nuclear plant, and they, that was sarcastic. And so, you know, they're like, how do you know this? How do you know we're having problems? They knew they were having problems. They didn't know the grid could see the problems. They didn't know they were imposing a problem on the grid. And it turns out to be a steam valve. There was a steam valve that was just fluttering. It wasn't seated properly. It didn't know if it should open or close. It was in this unknown area. And that's why when they increased steam pressure to get more output of the unit as it was going up, it would seat properly and the oscillation would go away. But in this no man's land, and this was a setting issue. This was not a faulty, but it was the wrong setting. The steam valve was just fluttering and it was causing the unit to oscillate. So that's what happened here. They went in and fixed the setting for the steam valve, narrowed its margin on the controller, and that fixed it. So, has anybody heard of this oscillation event? I'll make sure. Okay, I got about 20 minutes. So, I am chairing the Synchronized Measurement. It used to be Synchronized Measurement Subcommittee. Now it's NERC Synchronized Measurement Working Group. And that's what this group does. It looks at synchro phaser data for big oscillation events. Doesn't even, I say big. It could be something I just showed, you know, that maybe where you're experiencing an oscillation that could impact TVA, but maybe it impacts Duke or Southern or somebody around us. Well, I was vice chair here. I got a call this morning, January 11th, at about 3:30 from an operator, one of our TVA operators, and he said, "Hey, I don't know what's going on. I think we just had a grid oscillation, but everything's going crazy." And of course, I'm trying to get my bearings. I was asleep, and I asked a few questions. Well, did we trip a unit? Did we open or close a transmission line? Did we bring a unit up? January, we usually hit our peaks 7 o'clock in the morning, 8 o'clock in the morning when people are starting to turn their heaters on and lights and get ready for school and work. But this was still, you know, at 3:30 in the morning, and none of that had happened. No transmission line work, no units they were bringing up. And so we didn't know what was going on. So I was like, well, let me get my bearings, get out of bed, and I started working on the computer, pulling PMU data, Synchro Phaser data. And went into work and started looking at it. Well, later that morning, this is what I looked at RTDMS, and we've got alarms. All of the ones that are shown are on our 500 kV system. Remember, I told you we had two main voltage levels, 161,000 volts and 500,000 volts. the PMU devices shown in alarm here are on our 500 kV system, which tie hard to Southern, Duke. They're a backbone, not just for TVA, but for the whole Eastern Interconnect. That's how big chunks of power flow. So all of those went into alarm that morning. This is a video that UTK put together. It's for their FNET system. They use FDR's frequency disturbance recorders. That's where these little dots are. Those are PMUs. You may have heard about them, you may have not, but they deployed these several years ago, and they plug into an outlet just in your home, and they monitor the voltage at your house and the frequency, which is fine because all of these oscillations, most likely even if they're local, if you're close, you won't see it in your lights or on some of your equipment, but some of these devices can pick up these oscillations from just your outlet. So all of these little red dots are those frequency disturbance recorders plugged into somebody's outlet at home. And so that's the beauty of this because they're all time aligned. Remember, Synchro Phaser data, the key is they're time aligned. So you know what the voltage is here in Memphis at 0800, and you know what it is here in New York at 0800 at the voltage here. So when you put them all together, and this is where the industry is going beyond these frequency disturbance recorders where we all share our PMU data. Right now, we have all data for TVA, and it does great for TVA, but we need to know how it does with MISO or Southern Company or Duke when we put all of our PMU data that's using the exact same GPS signal. So this is what happened that morning. This is frequency. It's monitoring frequency from those little devices that plug into your outlets. And this is a contour map showing the frequency change. So you'll see what happens here when it gets in that area. And this is what our operators were seeing. Even Scada data was showing crazy stuff. And this was, it put a lot of people in a tizzy. Operators in our group, operators in Duke, operators up in Maine, operators in Florida. Okay, did you see that? You can see something's happening here in Florida. I gave it away. I was going to ask you where you thought it originated from, but you can see the frequencies dipping hard here and then going up and dipping and then going up. And then look up here around Wisconsin, Minnesota. You see this? They're responding to each other. So that was what we call a resonance effect. There was a unit here in the Fort Lauderdale, I've already forgot where, I think it was Fort Lauderdale. It's been so long. No, it wasn't. It was Tampa. There was a unit in the Tampa area that was oscillating because it had lost a voltage signal to its controller. And it didn't know how to control the output of the unit. It lost its reference. Yes, this power load imbalance, wherever it's at here, feeding into this controller, it had lost its voltage signal. So again, it didn't have a reference, and it was trying to control the output of the unit, and it didn't know, what reference signal. It didn't have a great reference signal because it lost one of the phase values. So it started oscillating up and down, megawatts going up and down, and people were like, "Oh, that must have been a huge unit, 1,000 megawatt unit." Nope, it was a 200 megawatt unit, which is not small, but compared to some of our bigger units, nuclear units, that is small. This little unit was swinging the whole grid. And the reason is hopefully y'all studied some of this, a resonance effect, right? Everything has a natural frequency. This podium has a natural frequency. Have y'all seen the swinging bridge video where the wind blows across it and it gets in sync and then it destroys the bridge? Same principle, resonance. there is a natural frequency that the group I'm on helped identify. There's 4 for the whole grid, and it's made up of all of our transmission lines or units, and one of those natural frequencies is the frequency that this unit was oscillating, 0.24 hertz. Actually, this was 0.25. The natural frequency is around 0.24. So it was really close. So this unit's oscillating at 0.25 hertz, and it starts exciting this natural mode that's just made up of, you know, the transmission grid, and it gets amplified because of this resonance effect. So that's why this little 200 megawatt unit in Florida was moving the whole grid. What was interesting is we went back and listened to some of the calls, and of course the operators in Tampa are like, yeah, we're having problems, but this is a little unit, you know, we're not causing this up in Wisconsin, we're in Florida, you know, don't you know that? You know, and turns out when they tripped the unit, because they were having so much trouble controlling it, because they didn't know at the time that that voltage signal had dropped and that their controller was going haywire. But when they tripped the unit, manually tripped it, all of this went away. So we were able to go back and say, when did you trip the unit? Here's the oscillation times. You know, when did you start experiencing problems? Because they knew they were having problems. They just didn't know they were shaking the grid. And so we were able to go through several days after and piece all that together. It's scary. Yes?
Were the residents affected by this?
I don't think so. Not at that time. That's a great question. I don't believe so. Not across the grid, because it was caught so quick. Eventually, our operators were calling Duke. Hey, are you seeing this? Yeah, I'm seeing this. Where's it coming from? Is it your unit? No, it ain't our unit. And eventually, we talked to Southern, they talked to Florida, and it was like, we got word back, well, they have a unit misbehaving, but they don't think it's them, you know. But here's where we were at. We had units moving in Mississippi and even in West Tennessee, because our units were trying to adjust to all the frequency variations, right? They're trying to control frequency. So our units are going up and down, up and down. And we thought our units were causing the problem. Our units were just responding. They weren't causing the problem. They were doing what they're supposed to be doing, regulating frequency. And so we were on the cusp of starting, and I say we went back several in the American Transmission ATC area. We're looking at tripping units, ComEd, and we were all about to trip units because our units were, we could tell they were getting hammered, going up and down, which is not good on a unit. And we didn't know, we either knew they were following and there was going to be damage, or they were causing it. Both were bad. So we had operators, we went back and listened, we had operators, balancing authority operators at TVA saying, we're about ready to cut this unit, we're about ready to trip it. So you start cutting a lot of units, you will put people in the dark. So we didn't get to that point, but I would say every time I present on this, you know, even at NERC, I'd say we didn't, but we were close. And people start squirming in their seat because this could have been bad. I mean, I don't want to say it could have been a blackout, but if this would have kept going, you could just see how it was starting to get worse and worse and worse. And you're going to have units that are going to start tripping on their control system, saying, I'm going out of bounds here, I'm going to trip, you know, or you're going to have operators manually trip units. And if you don't have enough units running to meet, you know, my load, your load, all of our air conditioners or heaters at the time, then bad things happen. Any questions on this?
Have anything been institutionalized where every plant knows its frequency compared to the local frequency or the area frequency?
So that's right. That's a great question. The group I chair developed a couple of papers saying, here are, let's see if I have it in here. I do. Well, I don't have them all. This is what the unit was oscillating at. This is one of the natural frequencies that we identified. There's 4 we identified for the Eastern Interconnect. We create a paper to disseminate across all the balancing authorities and the reliability coordinators for the Eastern Interconnect, and said, be aware of these 4 natural frequencies. Now, an oscillation's bad, right? When we were looking at this, Brown's Ferry, this is bad, but it stayed local. It was 0.5 hertz. We don't have a natural mode that we've identified around 0.5 hertz. So the only thing that's going to damage here really is just our unit, which is bad, but we're hopefully not impacting others, that, you know, like Southern and Duke that tie to us. So, but the main point is the paper was really to call out those 4 natural frequencies so that if you were to have a Brown's Ferry start oscillating at 0.25 hertz, you better know you could start moving the whole grid. So it's to kind of provide that awareness. Now, in the future, we want more of that to be embedded in the industry to where they have control mechanisms that if you start oscillating at that, you get heightened alarms or your plants know about it. It's very new, so we're all still trying to learn. But yes, those 4 natural modes are very important. WEC, the West, they have several natural modes. They're experts on power issues. That's probably a bad way to say it, but on oscillations, they have you know, we said here unnamed. Oh no, we did name it. So we named it Northeast, Northwest, South. What a great name, right? They have more detailed names for their natural modes because they have them so often. You got long transmission lines, and you're more susceptible to these type of oscillations. The Eastern Interconnect is very intertwined, and so we're not as familiar as this. This is all relatively new for the Eastern Interconnect. The WEC area, they've been dealing with this since, well, a long time, but they've known about it since the 90s. The 90s is where they started having big oscillations. So, okay, let me just touch on this. Solar, everybody talks about solar. Solar. TVA's putting in a lot of solar, and one of the problems we've had is oscillations, solar oscillations, controllers on the inverters not being set up correctly. So this is an oscillation we had last summer, and I won't go into all the details here, but this is Synchro Phaser data, just like we've been seeing, and it's for the output of the plant. And you can see something crazy is going on, right? It's pretty stable. Whoops, man, I gotta quit touching that. Pretty stable, oscillates, stable, oscillates. So we knew something was wrong here, and that's the megavars. This is the megawatts from this solar plant. It's a 270, I think, megawatt solar plant, which is pretty big. I mean, that's a lot of acres. And anyway, you can see that this is starting to oscillate. Wait a minute, is this the right one? Yeah, I'm sorry, this is megavars. But the point is, it's very systematic here. It's uniform, and this was a control setting. And what's crazy, what's shown on this map, that solar plant's right here. You're talking about customers. We had customers complaining about these oscillations. Everywhere there's a dot, we could see it with other instrumentation. Now, we didn't lose any customers, but they could see it. You know, what's going on? My voltage seems erratic. So that's why you got to be careful. If you tie even a solar plant to the grid, you can cause problems in a large area. So a lot of goals here. I'm not going to go through them for the sake of time. Any questions on this? Yes.
How does residential solar affect the oscillation? I know a lot of people now are trying to go solar for their houses and stuff, and essentially you're backfeeding the grid.
That's right.
To save power for their houses.
That's a great question. I would like to say I knew all the answers, but I think it's so new still. We don't have a great understanding. I think it's so small, and it's behind a high impedance with, a lot of transformers getting down to your house, and I think it's less likely to cause problems, but it's still, in my mind, it's an unsteadied state, unsteadied territory. And as you're right, as a lot of us start adding that, that's going to be a bigger unknown, because it may not be that it causes problems, but it may be that it reacts. If your voltage starts dipping and rising, you may have your controllers for your solar, following that and either dampening out that oscillation, which would be good, or you may have this resonant effect where, it starts swinging with it. So there's still, in my mind, a lot of unknowns.
Was this solar tied directly to the plant and at what voltage level?
Yes, at 161 kV. Yeah, yeah. This is a big solar plant, and we're putting more and more of those in. And we have that type of visibility with PMUs where we can see it. You know, at your home, not as easy to see, but this we can definitely see. Okay, what's going on here? So, okay, this is the most important thing. Everything else is not that important. I just mentioned, but the internship at TVA. So again, I would highly encourage you to look into the TVA internship. It's gotten better. Even 20 years ago when I did it, it was great, I thought, but it's gotten better. James, how long have you been? You've been since fall?
October.
Yeah, I was thinking the fall. We have some interns that have been in their position for 3 or 4 years. They started when they were freshmen. So if you're interested, these are the requirements. They will have copies of these slides, so you'll have this in there. GPA, you know, you got to have 30 credit hours. We do background checks, but so a lot of times freshmen may not be eligible because of the credit hours, but sophomores usually will be available or meet the requirements. There's a big, the pandemic has hurt us on the internship program in some ways. In some ways it's helped us. We used to have a lot of events where we'd go to a Lookouts game. All the interns would go to the Lookouts game or go to the Southside Social, or, you know, where you can network and get to meet managers and other interns. And pandemics put a damper on that. But we have interns now that can work remotely, and you don't have to come in the office as much, or maybe not at all, depending on what group you're interning in. So you can just work from home. Even if you're going to school, you know, you're taking, I don't know, 15, 17 hours, you can work 10, 15, 20 hours at TVA a week, you know, on mostly your time, depends on what group you're in. But that's the beauty, one silver lining of the pandemic, is we've relaxed interns working remotely. Used to, most of them had to come in the office, but now you can kind of work like I've got, so James is in our group, and then Matt is in our group, and he's going to school at UTK, but you know, he's working remotely as an intern. So that works out well for not just the summer internships, but spring and fall. We have classes, resume interview, our resume development interviews. We've started a capstone project. Let's see, so that started before you came in. We did one last summer. We'll be doing one this summer. I led it for transmission. And we had 3 transmission projects. One of them was visibility for Synchro Phaser data, which I think a lot of the students really enjoyed, but we're starting to implement more projects. I bet you're like, oh, not another project. But this is a good project because you don't get graded on it and you learn a lot, you know, so that's something we're trying to do more and more on, is have these projects where you get to meet other interns, learn more about TVA, so, and then working with engineers. You know, a lot of our interns get to work with engineers and attend a lot of meetings, which may not be fun, but you get to see what happens on a day-to-day basis at TVA. So key dates, if you're interested in the summer internship, which is May to August, you can go out to tva.com/careers and apply for summer internship. And make sure you apply by March 15th. And then for the fall, you have to apply by April 30th. The fall semester is September to December. And then we also, of course, will do spring. So that's what James is in now. So here it is, tva.com/careers, and here's how it shows up. Summer 2022 engineering internship. You click on it, it brings up the application, and you apply. So I can't stress this enough. It gives you, even if you don't work at TVA full time, but it gives you experience, you know, and you know, it helps build your resume. So I would highly encourage it if you're interested at all. Okay. Any questions on any of this, internships or Synchro Phaser data? I know I've run us almost long. Yes?
I do have another question. How
Sure.
long does PMUs last for? Because most of the time, a lot of this stuff does have like a
It is a very good question. So, you know, a lot of our relays, and y'all, if y'all haven't had relay classes, maybe you will, or you've heard about them. I mean, you know, TVA's got technology out there that's 60, 70 years old that's still in service. We have a lot of electromechanical relays, and that's why I laugh, because those things are indestructible. They're mechanical, but they're very simplistic, and they last forever. And then we put in these computers in a box for an ABB, GE, Schweitzer relay, and it may last 10 years because it's just like our laptops. They fail, you know. They're more intricate and they fail. So if you notice at the very beginning of the presentation, I had pictures of 3, and I said that one at the top, the ABB, we don't use anymore. It's outdated. We started installing those in the early 2000s from a grant. I'd say almost all of them. We probably had 20. I'd say only maybe 3 are still left. So those were kind of first generation utility grade, and they didn't last too long. Some of the ones we have now, I'd say they may be lasting 10 to 20 years. It depends. So that's a good question though. You gain a lot of flexibility and capabilities, I guess, with putting in boxes that can do all kinds of stuff, but it seems like they're just more delicate. Maybe that's because I'm used to seeing those electromechanical relays that 60 years old and there's nothing wrong with them. They may have asbestos in them, but you know, they don't mess up. So, any other questions?
Do you have to maintain a PMU cycle?
Yes. Remember, there's 3 things that pull into it: bus, PT, potential transformer, current transformer, and a clock. The PTs, the CTs, sometimes we have to tweak the ratio, what setting they're on, you know, depending on what band we're trying to measure. And then the clock. The clocks always seem to be a concern, like the antennas will go down, or somehow they'll get out of alignment and they'll start drifting. So yeah, it's not maintenance free, but it's still not bad. I mean, there's things you still have in the field. The field that maintains this, they're like, oh no, something else, I don't even know what it's doing, and I have to maintain it. So we've been trying to promote this more and saying, look, what you guys are doing, keeping this running, gives us this visibility for our operators. So they know now when there's an oscillation, and maybe they can prevent it or they can keep it from spreading, you know. So it's important to share how we're using this technology so that it's just not another piece of equipment that the field has to maintain. All good questions. Was this helpful? Maybe not. I don't know. Okay. Okay. Good. Gary Kilbert I worked with Gary for a while. Still work with him. He's not in my group, but he and I did a lot. I mean, he was kind of a founder of a lot of this at TVA. Then I picked it up, ran with it for 5 years. But you know, if you all know Gary, he's a sharp guy, and he can tell you a lot about this too. So you can ask him questions about this.
Can you draw this basic diagram that he normally shows for relaying?
Is it the Mo circle?
It's the same zone 1, zone 2.
Okay. Reverse zone 3. Yeah. I'm sure I've seen it. I used to sit beside him, and he had his own whiteboard, and he and I would draw a lot on that whiteboard. And I remember seeing a lot of Mo circles and distance relay diagrams. So.
They would teach us that in class when we went down to TVA. Okay, please try to sign in, and let's give Tim a...
Thank you. Thank you. All righty, thank y'all.